Hello and welcome to this new video where we discuss things mathematics and physics on the board. Now in this video, this is a follow-up from a previous video where we talked about integration in exterior calculus. Now in this particular kind of view, what we are going to do is first um, put some kind of reminders on what it is that we are doing, and then we are going to derive the famous, let's say, Jacobian transformation formula that we need to use and we have been told to use in many circumstances in physics and in applied mathematics and in pure mathematics as well, when we carry out multidimensional integrals. And we are going to see where this is actually coming from. Right, okay, so first of all, let's have a quick recap about some of the things we've seen in exterior calculus. I will put some kind of link somewhere to the previous video where I give some simple examples about how we go about integrating by using exterior calculus. And again, what we are going to see here, that plenty of the results and techniques that we've used or we have learned by heart to use essentially come from exterior calculus. And again, I'm not aware of any other way to actually treat it. Now, some people may say that they may come from a simple interpretation of how we carry out things in a Riemann integral, for example. Yes, that's true. But then in that case, in any case, the way of defining integration via a volume form is actually better suited. So let's take a look at first a recap of things. So imagine we've got a vector space uppercase V that is of dimension uppercase n. Okay. Now within, or not within, but on top of this, we can define a completely different object, which is going to be grounded in V in a sense, and this is called lambda kV, and that's the set of all so-called K forms that can be defined on V. And in this particular instance, because we look at calculus, then these forms are going to have coefficients here, omega I1 to ik, so there are K indices, and these omega are themselves scalar functions of a vector in V. At least that's the kind of tacit assumptions I'm taking here. So that's the kind of things that we're going to have. I've given some examples in the previous video about how that works, for example, in 1D. If you followed any of the videos I've done on the Hodge dual, then you've got also some appreciation about some ways to write these particular expressions here so that you don't forget any, but also you don't count twice the same ones. Now, one of the things we've introduced in the last video is basically the notion of n on the volume form. And the volume form is basically a K form, and which basically is an n form when V is of dimension n. So essentially that's the largest number of products you can take of vectors like this, of forms like this, without getting zero. Okay, if you try to extend that to any other, let's say, basis vectors that are like this dx, then you're going to get zero because you're going to have a doubling of any of them. Okay, so that's basically the kind of smallest one we can make, or the largest one, sorry, we can make. And it turns out that this is related to the volume of a cuboid. At least that's one way to conceive of it. It's related to the volume of a cuboid, whereby the corresponding volume you would get here is dx times dx2 times dx3 times dxn. And where here you would have the length, for example, dx1, and here or the vector, if you will, of length dx1, dx2, and so on and so forth. Okay, so that's the kind of thing we're looking at, and this is called often the volume form or canonical volume form. Okay, just to say that this is the simplest and also the safest volume form to start from. Okay, and on top of this, what we have seen last time is a fundamental theorem of calculus, of exterior calculus. Sometimes this is called the Stokes theorem or generalized Stokes theorem, and we are going to see why in subsequent videos as well. And the way it reads is that if you've got a domain, omega, that is inside, so if you've got a domain, omega, that is in a subset of the vector space, and it has boundary d omega, which is also a subset of that vector space, not necessarily, by the way, a vector space itself. It can be a subset that is not a vector space itself. Then the integral of omega of d omega, where d is the exterior derivative of omega, is equal to the integral of omega over the boundary term, okay, over the boundary. And we've seen some very simple applications in the case of one dimension, and in fact in two cases for that one dimension, and in the case of calculating the area of a disk for the two-dimensional case. Now what I want to do is precisely doing this, is try to look at the case of the volume form in 2D, and so that's what we're going to see here. So let's say we've got a volume form in 2D. And the thing here is that we need to be a bit careful, because the formula I'm going to derive, yes, stems from the volume form, but it could be as well that if you start from any kind of form, then this particular the reasoning I'm going to lay out here is going to be valid as well. So it just depends where you want to start as your initial kind of form to carry out integrations and so on. But let's start by the traditional one. Let's say we've got a volume form which is omega, which is dx wedge dy. Okay, so that's the volume form in two dimensions. So that's volume form. I don't need to specify anything really additional. And then I'm going to imagine that I've got a coordinate transformation. So I've got a coordinate transformation that essentially goes from the pair x, y of variables onto, and in fact it has to be a bijection, x1, x2. Okay, so they are simply different coordinates. I don't know what they are. Basically, that's kind of it. Now, the thing is that what I can do is naively use the definition of the exterior derivative. So dx here can be interpreted as the exterior derivative applied to the scalar field x. So the way I want to do this is basically interpret x and y as scalar field, as scalar fields of x1 and x2. And so what I have is that I've got the zero forms x is equal to whatever, some phi x of x1, x2, and then you've got some y is equal to phi y of x1, x2. So these are some sort of functions, okay? So that's one way at least you can look at it. And so these are forms. And so then what I can interpret, therefore, so interpret x and y as scalar field, and therefore dx and dy as one forms stemming from application of the exterior, stemming from the exterior product, the exterior derivative, sorry. And so what that means is that we are going to get that dx is therefore equal to, well, I could write phi or phi x, but basically I can write the following: dx, dx1 dx1 plus dx2 dx2. That's one way you can write it. And you can also write, likewise, dy is equal to dy dx1 dx1 plus dy dx2 dx2. All right, so what I do then is I actually substitute these expressions in there. So I'm going to get that the volume form omega is still the same volume form, is equal to, so I've got dx dx1 plus dx dx2 dx2, and then wedge dy dx1 dx1 plus dy dx2 dx2, and then I'm done. So then I need to remember that this is a product, okay? So that's a product, so therefore I can distribute all of these terms. And I need to keep in mind, that's what I'm going to say somewhere here, that dx, that basically if I have for any form beta, we need to keep in mind that for any beta, and for any beta in lambda k of v, and in fact for any degree k, so that's for any k that is less than n, we've got that beta wedge itself is equal to 0. Okay, regardless of the degree we talk about. All right. So what that means here is that dx1 wedge dx1 is 0. dx2 wedge dx2 is going to be 0. So what I'm left with is going to be only the mixed terms. So I'm going to have dx dx1, and then I've got times dy dx2, and then this is dx1 wedge dx2, and then plus I've got dx dx2, and then I've got dy dx1, and this is dx2 wedge dx1. Okay, and here another thing that we need to recall is how the wedge product works. We've got that dx1 wedge dx2 is equal to minus dx2 wedge dx1. So what we end up having is that this is equal to dx dx1 dy dx2 minus dx dx2 dy dx1, and this is then factorized dx1 wedge dx2, which is, if you will, the new volume form, but then there is this prefactor in front of it, so if we want to write an equality sign for omega. Now, what this thing is actually really kind of doing is basically the following. So that's this thing we can recognize is actually the determinant of the matrix, and this matrix is called the Jacobian matrix. So this is this thing is called the determinant of, usually this is called J, and then dx1 wedge dx2. Okay, so that's kind of the idea, and the matrix J is actually the matrix J, where, so that's omega, and then J is actually equal to d, so this is going to be dx dx1 dx dx2, and then dy dx1 dy dx2, so that the matrix of the derivatives of the transformation, where we actually have the transformation from x to from the former to the latter here. Okay, and so basically that's the kind of thing that you get, and you've got this particular formula where you get the actual determinant of this particular transformation. Now, sometimes there would be, if you want to look at the volume form, people are going to say that you need the absolute value. If the goal is to use this particular theorem, in principle, these are actual forms that we integrate. And so I don't think necessarily that that holds, but the whole point is that it has to do with the orientation of the volumes we talk about. And in principle, if you start with an orientation of the volume form which is positive, you should end up with something that is maintaining this positive definiteness in the actual determinant, etc., that you get at the end. Now, what happens is simply that that's here in the case of two dimensions. What happens is that if you try to start, let's say, with dx, dy, dz, then you're going to see that you can you know, depending on how you want to write things, you're going to see that you're going to get the determinant. So for example, you can write dx dy, dx dy dz, and you do first the transformation with respect to dx1 and dx2. So you're going to get this determinant here. And then you do the transformation with respect to dz, which you're going to expand in the same fashion here. And as you do that, you're going to see that you're going to obtain essentially the determinant of a 3 by 3 matrix, which is going to be a matrix like this, with simply an additional column associated to the z variable, and then an additional row associated to the x3 variable, and so on and so forth. So essentially, this is something where once you have done it for the case 2, then you can, by induction, if you want really to prove it, you could show that by simply accepting this formula for n, you would essentially get to n plus 1 with essentially the kind of the definition of the determinant in this particular case. So essentially, that's really how this is working, and that's where this Jacobian is, the determinant of the Jacobian matrix is coming from. Okay, and that's something that has implications as well in general relativity in some of the places as well that we are going to see in a different video. So I hope that it gives a bit of sense of where these things come from, and please note that this particular formula is only valid in the case where we have the volume form. So if you are not dealing with a volume form inside a particular domain of a vector space, then you need to use something else. Okay, so that's it. I hope you found it useful, and it provides a bit of context of where this particular determinant formula comes from. If you've got any questions or comments, please let me know in the comment section, and otherwise see you in the next video.